Alrighty, so I don't know about you guys, but I had a good time in the geologic record, but we are all finished with it. We have talked all about the foundation of naturalism here, and again, it is found to be completely and utterly incompatible with reality. Every step that we've looked at does not stand, either in the midst of its fellow steps or on its own. So when we actually started looking at the physical evidence, when we looked at the fossil record and we looked at the geologic record, it comes as no surprise whatsoever that it matches up a lot more closely and a lot better with the biblical version of history than the naturalistic version of billions of years. So that kind of raises the question, if all this evidence is really pointing in the direction of the Bible and not against it, so where did all these billions of years come from? And why are they so important to the scientific community? And that's what we're going to explore in this section in radiometric dating. Nice little hourglass there. So if you have not already done so, please write down radiometric dating. That's good. So as mentioned in the past, whenever we have a quote that is unattributed to somebody, in this case, it is going to be going to this individual, Dr. Jim Mason, PhD in experimental nuclear physics. So obviously he has a wonderful background to provide some insight on this topic. So, why is a consideration of radiometric dating important? Well, while the Bible clearly teaches that the Earth is just about 6,000 years old, you add up the genealogies, there's very little wiggle room in between those, radiometric dating allegedly proves that the world is 4.5 billion years old. And most people believe this. And this is important because if these billions of years end up not being real, again, as I've mentioned a couple of times by now through the course of the semester, without that amount of time to work with, the Big Bang can't be real. It needs that vast amount of time to be valid. Same thing with evolution. If you don't have billions of years to work with, billions of years where all these changes can build up and you can get brand new animals, then it's just as good as sunk right out of the gate. So, what is radiometric dating all about? Write this all down, please. I will elaborate on this once you're done writing. So there's a work here. That's the equation. That's changeable. You should end up with one of those answers. Because you've got your well, and I can't tell you exactly what's going right or wrong, but you know, you've got your mass, you've got your starting speed, you've got your entry speed. So you can use
What's final time minus the minus these, is this the final
You have to write it. You're just missing one small thing. I can't quite tell you what that is, but I will say that the work you've shown is going to get you on a partial credit even if you have to do it. Yeah, because it's solar powered. You have to go in the back again under the lights.
oh my god.
Where are you headed after this one?
Food.
So yeah, there's going to be a fair amount of writing today, and this is the start of it. But when we're talking about radiometric dating, this all probably just sounds like nonsense to you. But
Please pardon the interruption. Demarie Redmond to the office, please. Demarie Redmond to the office.
So in order to really understand radiometric dating, you have to understand a little bit about radioactivity. So how would you respond if I told you that the chairs you're sitting in right now were radioactive? You wouldn't be surprised? I'd be surprised. So hopefully, if you believed me, you'd probably get up and get out of those chairs pretty fast. So, you know, what's this all about? Why would you respond that way? And when we say something is radioactive, what we mean is that the molecules, the atoms, the stuff that makes it up is unstable. Over time, they will decay into another element that actually is stable. So at least that's good anyway. That new element would not be radioactive then. But this process of changing or decaying, as I mentioned, from one element to another releases a lot of harmful energy. And of course, you know that energy as radiation. It's the reason for all the nasty things that are going to happen to you if you continue sitting in your radioactive chair. But it's this process of one element changing or decaying into another over time that gave rise to the idea that maybe you can estimate time based on this process. And that's where this all comes in. Yes? What's that? Is that why copper turns green? I don't think so. I think that's just like, I think that's kind of like a rust. Like how silver, you know, tarnishes over time. Probably something more like that. But when we're talking about this radiometric dating, you know, when I mentioned that you've got those radioactive molecules changing or decaying into non-radioactive molecules, we have names for those. The radioactive element it starts out as would be the parent, and then it decays into the new daughter element. Now, we can actually measure in a lab with very sciencey, sophisticated equipment how long it takes for half of an element to decay into the daughter element. So these half-lives are known for most radioactive elements. We call those isotopes, and that ratio can be used to estimate how long the object has been decaying. You can kind of think of it like an hourglass. You start with, parent elements, your radioactive elements, and over time they change or decay into non-radioactive daughter elements. And based on the ratio that you see on the top or the bottom at any point, you can estimate how long the hourglass has been running. And, by analogy, you can estimate how long that element has been decaying, how long it's been in existence. So just to give you a bit of an example here, I picked this example because the name is fun and because it has a half-life that's actually something we can comprehend. So seaborgium has a half-life of 30 seconds, usually decays into rutherfordium. So seaborgium is the parent, rutherfordium is the daughter. So how is this going to shake out here? So let's say you've got a block of radioactive seaborgium, and that makes you very popular. After 30 seconds, if 30 seconds is the half-life, that means half of this, the bottom half here, is now rutherfordium. So you can kind of estimate time with that. So after another 30 seconds, then this amount that used to be seaborgium, half of that is going to then be rutherfordium. So now you're left with 1/4 seaborgium. And after another half-life, after 30 more seconds, you're down to only half of that. And so on, and that's how you can estimate time based on this method. Yes?
How do you preserve radioactive elements?
Well, they just naturally decay, so you can't really do anything to stop that decay. The only thing that stops it is it decays into that new element, and because that new element isn't radioactive, it doesn't decay anymore. But yeah, you can't actively stop something from being radioactive. You can just wait for it to stop being radioactive. So let's just do a little bit of math here and see how this would work. So all you're doing when you calculate your times here is you're doing a little bit of cross multiplication. And you can see the equation right here. I'll just show you how that works. Let's say we come across a sample, and that sample has 2/3 seaborgium, and 1/3 of it is rutherfordium. We can use those proportions to estimate how long that sample has been in existence. So let's see here. So the parent divided by the half-life equals the daughter divided by the time. So the parent is seaborgium. We're finding 2/3 of our object being seaborgium. So in terms of decimals, that's 0.6 repeating. And that's divided by the half-life, which is 30 seconds. And that's equal to our daughter element, which we find 1/3 of. So that's 0.3 repeating. And that's divided by time. So the one thing you don't know in this equation is time, and that's what you want to solve for. So you just do a little bit of multiplying, 30 times 1/3, and then divide all that, thank you, by 0.66 repeating, and that would get you the total time that object or element has been in existence. And when you do that here, it turns out to be 15 seconds. So it's actually pretty straightforward in terms of the math here. So it's kind of like, what could possibly go wrong, right? Any questions on this? All right. You guys miss cross multiplication?
No.
No. So the thing with this is most half-lives that we use to date rocks and other things on Earth are much longer than that of seaborgium. So these are different rock dating methods here, and you can see that they'd be used for different purposes. Potassium, the parent element, decays into argon, and its half-life would be 1.2 billion years. Uranium decays into its daughter element lead, and that would take 4.5 billion years. Rubidium to strontium, samarium to neodymium, and you get the idea. So obviously we have not been there over 1.248 billion years to observe, one full block of potassium decay into half a block of argon. So what we're doing in order to come up with these numbers is we're analyzing the decay rate with our very sophisticated scientific equipment. And when you look at the samples, this is just what would come back. If the entire sample decays over all time at the rate we're currently seeing right now in the present, it would lead to a half-life of this, and then this, and this, and this for those different elements. You can probably see where this is going. So, as you can probably guess, before using any measurement, instrument, or technique, it is good practice to calibrate it against some known quantity to ensure accurate results. If we're going to actually believe that this method is going to give us correct answers, we want to make sure that we can test it against something that we actually know the age of so that it can corroborate the idea and the theory and the methodology. For radiometric dating techniques, the obvious approach is to use the technique to determine the ages of some rocks of known age. So we've known how long some rocks have been around because we've seen them being created through lava flows and things like that. And this is one such example. In 1998, 8 samples were taken from 3 different past lava flows from Mount Naruhoe in New Zealand. I know that is the correct pronunciation because I looked it up. So, again, this is when we dated these rocks. With our fancy scientific radiometric dating equipment, we plopped these samples in the machine so that we could see how old those ages would come back. So, if these 2 samples of rock were created in 1949 from a lava flow, what should our radiometric dating machines have spit out for an answer here? So again, the rock was made in 1949, we know that. We dated it in 1998. What about should be the result then for how old it should come back as? So, yeah. So, because this is about 50 years before we dated the rock, hopefully we would come back with 50 years as the result from this radiometric dating. From 1954, obviously, that should be 40-some years old, and from 1975, that should be 20-some years old. Do you suppose those answers came back that way?
No.
Let's see how they came back. Give you a minute or two to just sort of digest that. So again, this was 2 different rock samples here, 4 different rock samples here, 2 different rock samples from there. And, yeah. These results are awful. Absolutely horrible. And I mean that for 2 reasons. Number one, they're obviously inaccurate. None of them say anywhere close to 50 years, although technically this isn't wrong and this isn't wrong and this isn't wrong. But they're also inconsistent, right? This sample that was taken in 1954, of those 4 different parts of that sample, you're getting a range of ages from 0 to 3.5 million years. So that's the worst kind of results that you can get back, where they're not only inaccurate, but inconsistent. Go ahead and write this one down, please. You don't need to write this down up here, just all the stuff on the left. Obviously, you'll want to leave some space to the right of all of those.
How much space do we need?
Just a little bit. You'll have maybe 6 or 7 digits of numbers after those. Very good. If you misspell the words, that's okay. Main thing is that you get the main idea from this slide. So the samples that we're looking at here come from a mountain that's a lot easier to pronounce than the last one. So this is from Mount St. Helens. It erupted in 1980, but since that time, it still was, kind of erupting, and lava was still creating lava domes. And in 1984, a lava dome was created that made all sorts of rock that we know the age of because we saw it being made in 1984. And unlike the previous example, when we radiometrically tested these samples, we did not just use one method. So the whole rock method is using the entire sample, impurities and all, and chucking that in our machine and seeing what dates pop out. Here we wanted to be more specific. So we also used some individual minerals and isolated those. That's where the feldspar, the amphiboly, and the pyroxene come in. So let's see if our results come back any more accurate here. Now, what results should come back? 1984, 1996. 12 years, right? Yeah. So we tested them in 1996. The rock was made in 1984. So hopefully you get a result of, 12 years, or at least something less than millions of years. Let's see what happened. And you're going to want to write those down. So are these results any better? No, they're not. You can see we don't even have any answers that say less than, 270,000 years like the previous example. So regardless of whether we use a whole rock method or individual minerals or anything in between, we regularly get results like this back from rocks that we know the ages of. So folks, it goes like this. If we test these rocks and we're getting these inaccurate results back from rocks that we know the ages of, then why should we trust results that come back for rocks that we don't know the ages of? It doesn't make any sense. If rocks of known age come back with bad results, why should we trust the results that come back for rocks of unknown age? So the question kind of becomes, how is it that this is so inaccurate? It seems like a very straightforward method. And this is where I want you to write all this down again. This could be probably is the most important slide from this whole section. So make sure you get all of this. And there's a little bit more to this as well that I look forward to sharing with you in a few minutes. So again, this method seems very straightforward. We can measure these decay rates very accurately in the lab. And the math ends up being very straightforward, just a little bit of cross multiplication. So what could possibly go wrong? And the answer to that is the fact that you have to assume so many things that there's no way to prove. Now, that you wrote down 3 assumptions here, but there are really way more than 3 assumptions that go into this. So I'm going to need some help from you guys in order to identify how many things we need to assume under these conditions. So here's what I need you to do. Every time I pause, you need to say the next number in line. So we're going to start with the number 1. When I pause the first time, you say loud and proud 1. And the next time I pause, you say 2. And then 3. I want to hear this louder than the other class, okay? So, here is what we have to assume in order to believe that radiometric dating gives us accurate results. You have to assume you know the starting conditions and how much parent element there was. You have to assume you know how much daughter element there was at the start. You have to assume the decay rate has been constant over all time.
3,
You have to assume no parent element was added to the system since the start.
4,
You have to assume no parent element was subtracted since the beginning.
5,
You have to assume no daughter element was added to the system.
6,
You have to assume no daughter element was subtracted from the system.
7,
That's 7 assumptions, and we can't go back in time to check the validity of these things, which is why this method does not hold water in the end. You have to assume lots and lots of stuff to be true that you can't go back in time to test. And that's where the floor kind of falls out on this. None of these assumptions are scientifically verifiable for rocks that are thought to be millions of years old. These all relate to things that have happened in the past, so there is no way of knowing whether they are true. The fact that radiometric dating ages for the given rocks of known ages turn out to be so seriously inaccurate is a strong suggestion that one or more of these assumptions is incorrect. I think that's a pretty good place to stop for today, but we'll pick it up here next time. Thank you for those loud numbers. I appreciate that.